Welcome to our comprehensive guide on electricity and magnetism for ICSE Class 10. In this video, we'll explore the fundamental concepts that form the backbone of modern physics. Electricity is all around us, powering our homes, gadgets, and industries. But what exactly is electricity? How does it flow, and why is it so important in our daily lives? We'll start by understanding the basics, setting the stage for deeper exploration into currents, circuits, and the mysterious world of magnetism. Let's embark on this electrifying journey together, making complex ideas simple and relatable for everyone. Electric charge is a fundamental property of matter, much like mass or volume. It's what causes objects to experience a force when placed in an electric field. There are two types of charges, positive and negative. Like charges repel each other, while unlike charges attract. This simple rule explains a lot about how electricity behaves. Think of static electricity. When you rub a balloon on your hair, the balloon picks up extra electrons and becomes negatively charged, sticking to walls or attracting small pieces of paper. Understanding electric charge is the first step in mastering electricity. Not all materials allow electricity to flow through them. Conductors are materials that let electric charge move freely. Metals like copper and aluminum are great examples. On the other hand, insulators such as rubber, glass, and plastic do not allow electric charges to pass through easily. This distinction is crucial in designing electrical circuits and devices. For instance, wires are made of copper, a conductor, but coated with plastic and insulator to ensure safety. Understanding the difference between conductors and insulators helps us use electricity safely and efficiently. Electric current is the flow of electric charge, typically carried by electrons in a wire. When you flip a switch, you complete a circuit, allowing current to flow and power your device. The unit of electric current is the ampere A. The direction of current is considered from positive to negative, even though electrons actually move from negative to positive. This flow is what lights up bulbs, runs fans, and charges your phone. Grasping the concept of electric current is essential for understanding how electrical devices work. Potential difference or voltage is what pushes electric charges through a circuit. It's like the pressure that drives water through pipes. The greater the potential difference, the more current flows. Voltage is measured in volts V. Batteries and power supplies provide this push, enabling current to move through wires and components. Without potential difference, there would be no flow of electricity. Understanding voltage helps us design circuits that work efficiently and safely. Ohm's law is a fundamental principle in electricity. It states that the current flowing through a conductor is directly proportional to the potential difference across it, provided the temperature remains constant. The formula is V equals IR, where V is voltage, I is current, and R is resistance. This law helps us calculate how much current will flow in a circuit for a given voltage and resistance. It's a cornerstone for solving many electrical problems and designing safe, effective circuits. Resistance is the property of a material that opposes the flow of electric current. It's measured in ohms omega. Think of resistance like friction for electricity. It slows down the movement of charges. Materials like nichrome have high resistance and are used in devices like heaters, while copper has low resistance and is used in wires. Factors affecting resistance include the material, length, thickness, and temperature of the conductor. Managing resistance is key to building efficient electrical systems. Series circuit components are connected end-to-end, so there's only one path for current to flow. If any part of the circuit is broken, the entire circuit stops working. The total resistance in a series circuit is the sum of all individual resistances. Series circuits are simple to design but have limitations. If one bulb goes out, all bulbs go out. Understanding series circuits helps us see why some devices are wired the way they are. Parallel circuits offer multiple paths for current to flow. Each component is connected across the same 2 points, so if one path breaks, the others keep working. This is why household wiring is done in parallel. If one light goes out, the rest stay on. The total resistance in a parallel circuit is less than the smallest individual resistance. Parallel circuits are more complex but offer greater reliability and flexibility. Electric power is the rate at which electrical energy is consumed or produced. It's measured in watts W. The formula for power is P equals VI, where P is power, V is voltage, and I is current. Power tells us how much work an electrical device can do in a given time. For example, a 100-watt bulb uses more energy per second than a 60-watt bulb. Understanding power helps us choose the right appliances and manage energy consumption. An electric current flows through a conductor. It produces heat. This is called the heating effect of current. Devices like electric heaters, toasters, and irons use this effect to function. The amount of heat produced depends on the current, resistance, and time for which the current flows. The formula is H equals I²Rt. This effect is both useful and something to be cautious about, as excessive heating can damage circuits or cause fires. Electric fuse is a safety device that protects electrical circuits from excessive current. It contains a thin wire that melts if the current exceeds a safe limit, breaking the circuit and preventing damage or fire. Fuses are used in homes, cars, and electronic devices. They are simple but effective, and understanding how they work is crucial for electrical safety. Always use the correct rating of fuse for your appliances. Magnetism is another fascinating force of nature, closely linked with electricity. Magnets have two poles, north and south, and produce a magnetic field around them. Like poles repel, unlike poles attract, similar to electric charges. Magnetic materials include iron, nickel, and cobalt. Magnetism is essential in many devices, from compasses to electric motors. Understanding the basics of magnetism sets the stage for exploring its connection with electricity. Magnetic field is the region around a magnet where magnetic forces can be felt. It's invisible but can be visualized using iron filings which align along the field lines. The strength of the magnetic field is strongest near the poles. Magnetic fields are not just limited to magnets. Electric currents also produce magnetic fields, which is a key concept in electromagnetism. Do you know the Earth itself acts like a giant magnet? It has a magnetic field with a north and south pole, which is why compasses work. The Earth's magnetic field protects us from harmful solar radiation and helps animals navigate. Understanding Earth's magnetism is important in geography navigation and even in studying the planet's history through magnetic rocks. Magnetic materials are those that can be attracted by a magnet. These include iron, nickel, and cobalt. Some materials, like wood or plastic, are non-magnetic and are not affected by magnets. Magnetic materials are used in making electromagnets, transformers, and many everyday devices. Knowing which materials are magnetic helps in designing and using electrical and electronic equipment. Electromagnetism is the study of the relationship between electricity and magnetism. When electric current flows through a wire, it creates a magnetic field around it. This discovery led to the invention of electromagnets, which are widely used in electric bells, relays, and motors. Electromagnetism is a cornerstone of modern technology, enabling everything from power generation to communication systems. Right-hand thumb rule helps us determine the direction of the magnetic field around a current-carrying conductor. If you hold the conductor in your right hand with your thumb pointing in the direction of current, your fingers curl in the direction of the magnetic field. This simple rule is essential for understanding how electromagnets and electric motors work. Electromagnets are magnets created by passing electric current through a coil of wire wrapped around a soft iron core. Unlike permanent magnets, electromagnets can be turned on and off by controlling the current. They are used in cranes for lifting heavy metal objects, in electric bells, and in various industrial applications. Electromagnets are powerful and versatile, making them essential in modern technology. Electromagnets have a wide range of uses. They are found in electric bells, relays, loudspeakers, and MRI machines. In industries, they are used to lift and move heavy metal objects. Electromagnets are also crucial in electric motors and generators, enabling the conversion of electrical energy to mechanical energy and vice versa. Their ability to be controlled makes them invaluable in technology. An electric current flows through a wire, it produces a magnetic field around it. This is known as the magnetic effect of current, or Oersted's effect. This discovery was a turning point in physics, showing the deep connection between electricity and magnetism. The strength of the magnetic field depends on the current and the distance from the wire. This effect is the basis for electromagnets and many electrical devices. Electric bell is a classic example of electromagnetism in action. When you press the bell switch, current flows through an electromagnet, attracting a metal arm. This movement rings the bell and breaks the circuit, causing the arm to return and repeat the process rapidly. This cycle continues as long as the button is pressed, producing a ringing sound. Electric bells are used in schools, homes, and offices. Electric motor is a device that converts electrical energy into mechanical energy. It works on the principle that a current-carrying conductor placed in a magnetic field experiences a force. This force causes the conductor to move, producing rotation. Electric motors are found in fans, mixers, washing machines, and countless other devices. Understanding the motor principle is key to appreciating how many modern conveniences work. Electric motor consists of several key parts: the armature, rotating coil, commutator, brushes, and a permanent magnet or electromagnet. The armature rotates when current flows through it, while the commutator and brushes ensure the current direction changes appropriately. Each part plays a vital role in converting electrical energy into smooth, continuous motion. Knowing the parts helps in understanding and troubleshooting motors. Electric generator does the opposite of a motor. It converts mechanical energy into electrical energy. It works on the principle of electromagnetic induction, discovered by Faraday. When a coil rotates in a magnetic field, it induces an electric current. Generators are used in power plants to produce electricity for homes and industries. Understanding this principle is crucial for grasping how electricity is generated on a large scale. Electric generator has several main parts: the armature, coil, slip rings, brushes, and a magnet. As the armature rotates in the magnetic field, current is induced in the coil. Slip rings and brushes help transfer the generated current to the external circuit. Each part is essential for efficient electricity generation. Knowing these components helps us understand how generators supply power to our homes. Electromagnetic induction is the process of generating electric current by changing the magnetic field around a conductor. Faraday's experiments showed that moving a magnet near a coil, or moving the coil in a magnetic field, induces a current. This principle is the foundation of generators, transformers, and many modern technologies. It's a key concept in understanding how we harness and use electricity. Faraday's law states that the induced electromotive force, EMF, in a circuit is directly proportional to the rate of change of magnetic flux through the circuit. In simple terms, the faster the magnetic field changes, the greater the induced current. This law is fundamental to the operation of generators and transformers, making it a cornerstone of electrical engineering. Transformers are devices that change the voltage of alternating current AC. They work on the principle of electromagnetic induction. A transformer has two coils, primary and secondary, wound around a core. By varying the number of turns in each coil, transformers can step up or step down voltage. They are essential for transmitting electricity over long distances and for safely using electrical devices at home. There are two main types of transformers: step-up and step-down. Step-up transformers increase voltage, while step-down transformers decrease voltage. Power stations use step-up transformers to transmit electricity efficiently over long distances, and step-down transformers reduce voltage for safe use in homes. Understanding transformer types helps us see how electricity is delivered safely and efficiently. Domestic electric circuits are designed to safely distribute electricity throughout homes. They include main switches, fuses, circuit breakers, and wiring arranged in parallel. This setup ensures that if one appliance fails, others keep working. Proper earthing and safety devices protect against shocks and fires. Understanding domestic circuits is vital for using electricity safely at home. 3-pin plug is a common electrical connector used in homes. It has 3 pins, live, neutral, and earth. The earth pin is longer and thicker for safety, ensuring the device is grounded before current flows. This design protects users from electric shocks and ensures safe operation of appliances. Knowing how a 3-pin plug works is essential for electrical safety. Earthing is the process of connecting electrical devices to the ground. It provides a safe path for excess current to flow into the earth, preventing electric shocks and damage. Earthing is a critical safety feature in homes and industries. Proper earthing ensures that in case of a fault, the current is safely diverted, protecting people and equipment. Short circuit occurs when electricity takes an unintended path with very low resistance, often bypassing the normal load. This causes a sudden surge of current which can overheat wires and cause fires. Fuses and circuit breakers are designed to detect and stop short circuits, protecting people and property. Recognizing and preventing short circuits is vital for electrical safety. Overloading happens when too many devices draw current from a single circuit, exceeding its safe limit. This can cause wires to overheat, leading to fires or damage. Circuit breakers and fuses are installed to prevent overloading by cutting off the current when it gets too high. Avoiding overloading is essential for maintaining electrical safety at home and in workplaces. Using electricity safely requires following certain precautions. Always use appliances with proper insulation, avoid touching electrical devices with wet hands, and never overload circuits. Regularly check wiring and replace damaged cords. Install fuses and circuit breakers for protection. These simple steps go a long way in preventing accidents and ensuring safe use of electricity at home and work. Static electricity is the buildup of electric charge on the surface of objects. It occurs when two materials are rubbed together, causing electrons to transfer from one to the other. This can create a spark or make objects stick together. Static electricity is responsible for phenomena like lightning and the shock you feel after walking on a carpet. Understanding static electricity helps explain many everyday occurrences. Lightning is a dramatic example of static electricity in nature. It occurs when charges build up in clouds and discharge suddenly to the ground, producing a bright flash and thunder. Lightning can be dangerous, so it's important to stay indoors during storms. Lightning rods are used to safely direct lightning to the ground, protecting buildings and people. Capacitors are devices that store electric charge. They consist of two metal plates separated by an insulator. When connected to a circuit, capacitors can store and release energy quickly. They are used in electronic devices to smooth out voltage fluctuations in camera flashes and in many other applications. Understanding capacitors is important for grasping how electronic circuits work. Magnetism has countless applications in daily life. It's used in compasses for navigation, in electric motors and generators, in MRI machines for medical imaging, and in magnetic locks for security. Magnets are also found in speakers, hard drives, and credit cards. The diverse uses of magnetism show how important it is in technology and everyday life. Magnetic storage devices use magnetism to store data. Hard drives, credit cards, and magnetic tapes all rely on this principle. Data is written and read by changing the magnetic orientation of tiny particles. Magnetic storage is reliable and widely used in computers and other electronic devices. Understanding how these devices work helps us appreciate the role of magnetism in information technology. Magnetic levitation, or maglev, uses magnetic forces to lift and move objects without contact. Maglev trains float above tracks, reducing friction and allowing high speeds. This technology is also used in some medical devices and scientific instruments. Magnetic levitation demonstrates the power of magnetism in creating innovative solutions for transportation and industry. Electromagnetic waves are waves of electric and magnetic fields that travel through space. Light, radio waves, X-rays, and microwaves are all examples. These waves are essential for communication, medical imaging, and many technologies. Understanding electromagnetic waves helps explain how information travels wirelessly and how we see the world around us. While magnets and magnetic fields are generally safe, strong magnets can be dangerous if not handled properly. They can damage electronic devices, pinch fingers, or interfere with medical implants like pacemakers. Always use magnets with care, especially around sensitive equipment. Understanding safety precautions ensures that we benefit from magnetism without risk. We've journeyed through the fascinating world of electricity and magnetism, covering everything from basic concepts to practical applications. Understanding these principles is not only essential for exams, but also for appreciating the technology that powers our lives. Remember, electricity and magnetism are deeply connected, forming the foundation of modern physics and engineering. Keep exploring, stay curious, and use your knowledge to make the world a safer and smarter place.